Hello, and very good evening to all of you. Okay, so um, today we will be continuing with our lecture session again lah. Okay, so this lecture today we will be jumping into a new chapter. Okay, we'll be jumping into a new chapter, which is chapter 5 lah. Okay, in chapter 5, okay, we will be learning about, or we'll be jumping into thermodynamic processes. Okay, so without further ado, let us start our lesson for today lah. Okay, so after this chapter, I can say we have completed all our lessons lah for basic thermodynamics. Okay, alright. So without further ado, let us start lah. Okay, okay. So this is the overview of this chapter lah, chapter 5, thermodynamic processes lah. Okay, so let me explain lah. Okay, so what is the definition of thermodynamic processes? Okay, so it is a system transformation from one thermodynamic state to another, involving changes in macroscopic variables like pressure, volume, internal energy, and temperature. Okay, these processes represent the path a system takes as it exchanges energy, often as heat or work, and are fundamental for understanding how energy is transferred and converted in a system. So basically, thermodynamic processes, okay, discusses about the exchange of energy lah. Okay, exchange of energy, how it is transferred or how it is converted. Okay, so what is the importance of thermodynamic processes in practical applications? So here are the list lah of the importance of thermodynamic processes. So one of it is thermodynamic processes are fundamental in many applications, especially in field of engineering, energy, and environmental science. Next, thermodynamic processes helps engineers and scientists to improve energy efficiency, design and optimize systems, and solve complex problems. So this is the importance of thermodynamic processes. Okay, next, energy conversion and efficiency. So thermodynamic processes are the heart of energy conversion system. Okay, such examples that use energy conversion systems are the heat engines, refrigerators, and power plants. By understanding the laws of thermodynamics allows engineers to maximize efficiency in 1. Internal combustion engines, for example in cars, aircraft, and power plants. Next, refrigeration and air conditioning systems. Next one, heat pumps for heating and cooling. Next, gas turbines in power generation. And last but not least, steam turbines in electricity generation and mechanical work. So, um, so basically by understanding, okay, this thermodynamic processes allows us to maximize efficiency. Okay, so being able to control and optimize thermodynamic processes means you are able to reduce the loss of energy, lowering fuel consumption, and improving the environmental sustainability of systems. Okay, next, design and optimization of power systems. Okay, in thermal power stations, okay, coal, gas, and nuclear lah example. Thermodynamic processes govern the conversion of heat into mechanical energy and electrical energy. Okay, the Rankine cycle example used in a steam turbine and Brayton cycle that is used in a gas turbine are examples of thermodynamic cycles that determine how efficiently a system can convert thermal energy into work. Okay. Okay. Next, the first law of thermodynamics that is that has relation to conversion of energy. Okay, helps us to understand energy input or output relationships. Okay. The next one is the second law of thermodynamics dictates that some energy will always be lost as heat and sets the upper limit on efficiency. Okay. Again, now next, refrigeration and air conditioning. Okay, so thermodynamics plays a crucial role in designing refrigerators, freezers, and air conditioning systems. The Carnot cycle and vapor compression refrigeration cycle are widely used to understand how heat is transferred from one place to another, providing cooling enclosed spaces. Okay? Refrigeration cycles depend on phase changes of fluids, for example, from liquid to gases and vice versa, to absorb and release heat. Okay? Engineers use thermodynamics principles to design systems that use less energy while maintaining desired temperature levels. Okay, so that is basically thermodynamic process lah. We want to design something, okay, in order to it'll be efficient and use less energy lah. Okay, okay. Next, environmental impact and sustainability. Okay. Thermodynamic processes are critical in designing systems that minimize environmental impact. Okay? For example, combustion processes in engines and power plants emit greenhouse gases. By understanding the thermodynamic principles of combustion, allows the design of cleaner, more efficient engines and reduce carbon emissions. Okay. Next, waste heat recovery systems aim to capture excess heat from industrial processes of power plants and convert it back into usable energy, reducing waste and improving overall system efficiency. Okay, so that is the environmental impact and sustainability of thermodynamic processes lah. Okay, so next is in terms of material and chemical engineering. Okay, so in chemical engineering, thermodynamic principle or process governs the reaction and phases of substance involved in processes like distillation, chemical reactions, and material synthesis. For example, in understanding the Gibbs free energy is essential for determining whether a chemical reaction will occur spontaneously under certain conditions. Okay, next, phase diagrams based on the thermodynamic principles helps in understanding material properties at various temperatures and pressures. Next, optimizing chemical processes relies on understanding energy flow and equilibrium state to improve yield, efficiency, and safety. Okay, next, space exploration. Okay, thermodynamics is also the key in design of systems for space exploration, including spacecraft propulsion, heat shields, and life support systems. The need to efficiently manage limited resources such as energy and materials makes thermodynamics crucial in these three aspects. First aspect is spacecraft propulsion using chemical or nuclear propulsion system. Next, thermal control systems to manage extreme temperature in space. Next one, life support system that maintains proper pressure, temperature, and oxygen levels. Okay, so this is the importance of thermodynamic processes in space exploration. So next, what are the type of thermodynamics processes? Okay, so there are several types of thermodynamic processes, okay, each describing how a system undergoes a change in state. These processes are classified based on the way parameters such as pressure, volume, and temperature change. Below are the main types of thermodynamic processes. Let me explain. So, first, one of the thermodynamic processes here is isobaric process, okay, also known as constant pressure. Okay, let me explain what is isobaric process. So, the definition of isobaric process is the pressure of the system remains constant, okay, while other properties like temperature and volume change. Okay, so that is isobaric process. Example, heating water in an open container when the pressure remains constant at the atmospheric pressure. Okay, so the mathematical expression is expressed here lah. So expressed here lah in this equation. So P is constant lah. It's constant. So this is isobaric process lah. So the pressure remains constant and the work done, okay, is equals to W equals to P delta V. Okay, so Q equals to delta U plus W. Okay, so this is the formula for isobaric process lah. Okay, this is the mathematical expression lah. Okay, so now next, one of the example of thermodynamic processes is isochoric process. So isochoric process is also known as constant volume. Okay, so let me explain what is isochoric process. So in isochoric process, the volume of the system remains constant, meaning no work is done by or on the system. The pressure and temperature can change. Okay. Okay. Now, next example: heating a gas in a sealed rigid container. Okay, so that is an example of isochloric process. So this the mathematical expression for isochloric process lah. So V being a constant, okay, volume remains constant lah. Okay, V is volume. So delta V equals to 0. Okay, so no work is done, meaning W is 0 lah. So Q equals to delta U. So this is the mathematical equation or equation for isochloric process. Okay, so next one. Next one is isothermal process or constant temperature lah. Okay. So what is the definition of isothermal process? So the definition is, in isothermal process, temperature of the system remains constant, meaning the heat exchange is fully used to do work or change the system's internal energy lah. Okay. For example of isothermal process is slow expansion or compression of gas in a cylinder that remains at a constant temperature. Okay, so the mathematical expression is T equals to constant. So T temperature is constant lah. Okay, so this is the equation for isothermal process. Okay, temperature remains constant, delta T equals to 0, temperature lah. Okay, internal energy remains constant. Okay, delta U equals to 0 lah, energy. So work done is W equals to Q. Okay. So next is adiabatic process. So adiabatic process, also known as no heat exchange. So what is the definition? Okay, in adiabatic process, there is no exchange of heat with the surroundings. So heat is represented by Q lah. Q is heat lah. Okay. So Q is 0. Okay, the system's energy exchange is entirely due to work done or by the system. Example can be seen here is a gas expanding rapidly in an insulated piston. No heat enters or leaves the gas. Okay, so that is example of adiabatic processes in our daily lives. Okay, so the mathematical expression is Q equals to 0 lah. So basically heat is 0 lah. No heat exchange. Okay, internal energy changes equals work done. Okay, so delta U equals to negative W. So typically occurs rapidly or in insulated systems. Okay. Okay. So we have learned about the types of thermodynamic processes already lah. Okay. So let me explain the first law of thermodynamics here to you. Okay. So what is first law of thermodynamics? Okay. This one is not alien to you. You know and you've heard about it. Okay. So first law of thermodynamics clearly states that energy cannot be created nor destroyed. It can only be transformed. So that is first law of thermodynamics. Okay. So the mathematical formulation for this law is delta U equals to Q minus W. Okay. So delta U equals to change in internal energy. Q is the heat. W is the work done. Okay. So the application is how it governs the conversion of heat to work in engines and other systems. Okay. So next is key thermodynamic quantities. Okay, so as you can see here, this is the quantities lah. Heat also is represented in Q. Okay, energy transferred due to temperature difference. Okay, work, which is represented by W, energy transferred when the force acts over a distance. Okay, next is internal energy, U, where energy contained within a system lah. Okay, so this is the quantities lah. Okay, so this the next is the work done by expanding gases. So this is the formula lah for work done by expanding gases lah. So work done is in various processes lah. So in isobaric process, the work done formula is W equals to P times delta V. Okay, for isochloric process, there's no work done, so work is 0. Okay, in isothermal process, work equals to N times R T times in Vf over Vi. Okay, in adiabatic process, work done equals to this formula lah. Okay, this formula here. Okay, so thermodynamic cycles. Okay, now next is thermodynamic cycle. So the definition is a sequence of process that returns a system to its initial state. So that is thermodynamic cycle lah. Okay, Example of thermodynamic cycles are Carnot cycle, Rankine cycle, and Brayton cycle. Okay, so each of these cycles involves a series of isothermal, adiabatic, isobaric, and isochoric processes. Okay, this one we have went through lah just now. Okay, so practical applications in engines and refrigeration systems. So all of this can be seen is applied in engines and aircraft and refrigeration system. Okay, so okay, next, thermodynamic processes in real world systems. Okay, this is an example lah. They can be seen in real world systems. Okay, as you can see, steam cycles. Okay, the work is done in power plants lah. Okay, in internal combustion system is the Otto and the diesel cycle. Okay, in air compressors it is adiabatic compression. Okay, can be seen lah. In refrigeration system it use vapor compression cycle lah. Okay, so this is the example of real world systems lah that use thermodynamic processes. Okay, so we have reached at the end of our lesson already. Okay, so that's all for our chapter 5 lah. It's a simple lah. It's talking about the thermodynamic processes lah. Okay, so if you have any questions, feel free to ask me. Okay, so I think that's all for our class for today. Okay, we have completed the whole chapter already for chapter 5. Okay, so the whole lesson for basic thermodynamics we have completed already. Okay, so if you have any questions, feel free to ask me. Okay, and later I will give tutorials to you. Please attempt the tutorials lah. Okay, so if I think later I'll give some tips also for your final exam lah. Okay, for your finals, and I give tutorials that will be useful for your final exam. Okay, so I think that's all for today. Okay, for our lesson. I think we will end our class here today. Okay, so thank you everyone for your time. I'll see you in the next lesson. Okay.